We, as a society, have been rapidly destroying our own environment for quite some time now, and we believe that if substantial changes aren't made now, we'll all slowly fall victim to the death of our beautiful planet. As future chemists and scientists, we play a big role in the demolition of Earth. With our carbon footprint history, we need to start looking into ways to be more climate positive and in hopes of reaching negative carbon emissions. This positive, environmental friendly movement is known as green chemistry, which is where chemists and engineers are creating cool scientific ways to try and reduce or essentially eliminate the production of hazardous substances through experiments that can overall affect our health as well as the environment. This prevention can come in many different forms and principles. Today we will be focusing more specifically on what we view to be the future of green chemistry. As chemists, we do a lot of experiments and produce tons of different types of chemicals. However, to get to manufacture such chemicals, we don't usually use the best resources. More often than not, these resources include scavenging underneath the ground for fossil fuels, coal, oil, etc., which may seem practical at first, but what happens when those sources deplete, when these materials no longer exist? This is why Principle 7 of the Green Chemistry Initiative, the use of renewable feedstock, was implemented. It is of great importance because in order to continue creating useful chemicals on larger scales, we have to be able to use other renewable resources that can be derived from carbon sources. Plants have proven to be an excellent choice for renewable feedstock. The carbon in the air gets utilized to form plants through photosynthetic processes. This is also known as biomass. The image shown here is an example of the cycle of biomass. As you can see, plants produce biomass through photosynthesis, using the CO2 in the air. This biomass can then be burned directly for heat or converted to renewable liquid and gaseous fuels. Through non-toxic means, we can engineer ways to use this biomass that we can achieve oils, starches from, and then in turn create useful base chemicals such as fatty acids, glycerol, glucose, and etc. However, we have to keep in mind the amount of carbon being exhausted when utilizing this biomass, as we don't want to increase our carbon footprint. This image here included shows that the carbon being used must be more than the carbon being exhausted when creating this biomass.
There are many ways that we see renewable feedstock being implemented in the real world as different scientists are trying to come up with new products they can create from feedstock. One of the biggest negative effects on the environment is aviation fuel, but because it is used and needed so heavily, it cannot simply be eradicated. Most jet fuel is currently being derived from crude oil, and seeing as there is a shortage of fossil-based fuel in the foreseeable future, making a new renewable feedstock alternative is beneficial for everyone involved. Some food crops such as starchy vegetables, nuts, lentils, grains, etc. are used to produce bioethanol and biodiesel. Biomass fuels absorb greenhouse gases such as nitrogen monoxide and carbon dioxide during the growth stage of the feedstock, and the amount of gases going in and through to the combustion is balanced. A lot of research is still being put into the feedstock oils to see what the best overall result is, but we hope to see more of it implemented soon. Another example that is actually being more and more implemented in today's society is renewable lubricants. With such high economic value, it's a great idea to have an alternative biodegradable option originating from triglycerides, wax esters, and plant polymeric carbohydrate. One of the most fascinating research being done that is oftentimes overlooked is the production of chemicals used in pharmaceutical manufacturing from renewable feedstock. Researchers Sekar, Mao, Locato, Wang, and Lee have discovered a way to develop Enantiopure R and S 2-phenylglycinols, which are crucial chiral building blocks involved in pharmaceutical manufacturing. Previously, a very complex method were used to develop the product. However, they were able to discover a one-pot simple synthesis from renewable feedstocks and other cheap materials. They were able to take the L-phenylalanine biosynthesis pathway they created and combined it with R or S enantioselective cascade and did this in one strain or a couple strains in order to achieve the first synthesis of R1A and S1A from a renewable feedstock.
Ideally, with this principle implemented, it would create a biofuel economy in which our carbon footprint is decreased, less toxic chemicals are generated, and an overall safer environment. However, it's not as easy as it sounds because there are different problems that arise when we try this method of biorefinery, and such that we have to develop a way to convert this renewable carbon source into the chemicals and materials we need. and as of right now, we lack the appropriate technology to do so. It is estimated that the future holds promise for this principle, as new advances in technology have stemmed through and several efforts of teamwork have been seen between different branches of sciences such as physics, biotech, engineering, etc. One can say that the future is definitely bright for green chemistry.